All right, so we were going to prove this proposition, which tells us that if we have a collection of connected subsets of a metric space, and if this collection has a common point, then the union of this collection of connected subsets is connected, and proof is easy. All right, let x0 be a point in this non-empty intersection. Okay, we are given that it is non-empty, so we have something like this. I have this point x0, and I have this subsets. Okay, e alphas, e alpha, e beta, and so on. Of course, this is a uh, not the realistic picture. It is just a model. But the thing is that if each of them are connected, and if they have a common point, then we see from the picture that the union is also connected. And the proof goes like this. Let A be open sets, subsets of X, giving a separation for the union. Okay. Well, then we would have what? Well, you see, then of course each E alpha would is a subset of this union, and this union is in A and B. But E alpha is connected. Since E alpha is connected, E alpha should lie either completely in A or in B, because if some part of E alpha would lie in A and some part would lie in B, then E alpha would be disconnected. So E alpha should lie completely inside A or B. So each E alpha lies inside A or B. But x0, on the other hand, this point x0 is in A and B, is in this intersection, and thus x0 is in A without loss of generality. Right? This point x0 is either in A or B, and without loss of generality, let's assume that it lies inside A. Now, each E alpha is either in A or B completely, but x0 belongs to each E alpha, therefore each E alpha should lie inside A. This implies that each E alpha uh, must lie in A. So the union must be in A, but this implies, and thus this union intersection with B is empty, because you know AB is a separation, means some part of A should be in A and some part of B should be in B, and no common point should lie inside A and B, right, of the union. However, if this whole thing lies inside A, then there would be no part of this which would lie inside B. Therefore, we would have this, and this is a contradiction. A contradiction. Okay. All right. Do you have any questions on this? Okay. Well, using this, we can uh, further obtain some examples of connected subsets of the real line. We know that the interval 0, 1 is connected, and therefore any continuous image of 0, 1 is connected. Uh, note that uh, for any interval AB, we have a homeomorphism F from 0, 1 into AB, given by, what is this? Well, it is A plus T times B minus A, right? When you plug T equals 0, you get A. When you plug T equals B, T equals 1, you get B, right? Well, since this is a homeomorphism, in particular, its image is AB. Okay, since 0, 1 is connected and AB is the image of F01, we see that AB is connected. So any closed interval, finite closed interval, is connected. Okay. But then any such, taking unions of such closed intervals, we can obtain actually any interval. Now, this implies that any interval I is connected. Why is that? Well, let me give you some examples. For example, let's take this interval. Okay, open interval. Let's say AB. Why this is connected? Well, this is connected because I can write this as the union of intervals of this type. A minus 1 over n, A, no, a plus 1 over n, b minus 1 over n. Okay, a, b. So what I do, I take a smaller interval like this, a plus 1 over n, b plus 1 over n, starting from some number and 0, so that it lies here. So 1 over n, I want this to be small so that, you know, this closed interval lies inside AB, and take its union till infinity. You see, as n goes to infinity, a plus 1 over n, so it is this point, a plus 1 over n, and this point is a minus 1 over n. Both of them converges, uh, approaches to the endpoints of the open interval, and their union is equal to this. And all of these contains a common point. Let's say this point here, some point like this. Okay. Actually, I can choose this point to be what? A plus b over 2. So, okay, I choose closed intervals. Now, these are all closed finite intervals, therefore they are connected. These are connected, and they contain the common point, the midpoint of the interval AB. Therefore, their union is connected. Is connected. What about other intervals like this? So this is, let's say, one example. Another one is, let's say, look at this one. Uh, Infinity. Well, this is connected because this can be written as what? A plus a comma a plus n, and from 1 to infinity, right? These are all connected and they all contain a, right? So x0, which is a, lie inside all of them. And this is connected. And this implies this is connected. And similarly, other intervals, we may check each kind of interval separately. They will be all connected, okay? For example, let me do a third one. An interval like this. Okay, let's say it is closed from one end but open from the other end. I can write this as how? A plus a comma b minus 1 over n, and from some point till infinity. So a, b, and this is b minus 1 over n. Okay. Okay, I should take closed interval here. Well, these are all connected, and they all contain x0, which is a, the common point, and therefore this interval is connected. Okay. So what we see is then any interval of R is connected, and we also have the following. If a subset is not an interval, then it cannot be connected. So this would give us the following theorem. A subset I of R is connected if and only if it's an interval. Well, we already seen that if it is an interval, then it is connected. So we have already seen that intervals are connected. So what I need to do is then, if a subset is not an interval, then it cannot be connected. Conversely, let I be a subset, not be a subset uh, which is not an interval. What do we mean by which is not an interval? What's an interval? Interval is a point so that whenever you have 2 points in it, anything between them also belongs to the subset. So this means what? Hence, hence there are points A and B in I, so that uh, this thing doesn't lie inside A. Not an interval means exactly this. Uh, it contains 2 points, but the interval between them doesn't lie inside A. Okay, say C is in AB and C is not inside I. So we have this. Sorry. I have something like this. A belongs to I, B belongs to I, but there is some point here, and this point doesn't belong to I. Okay? Well, uh, just let A to be minus infinity C and B to be C plus infinity, which are both open. Okay. I doesn't contain C, therefore this is a subset of R minus C, but that is just A union B. Okay. So this is the first condition for being a separation. Second, A is in A intersection I, right? This is in I, this is in I. Therefore, A intersection I is not empty. B belongs to B intersection I. Therefore, B intersection I is not empty. And the third condition that uh, I intersection A intersection B is empty. Well, it is because A intersection B is already empty. Okay. Hence, I is disconnected. So we proved what? We proved that the only connected subsets of R are just intervals. Okay, this finishes the proof. Okay. All right. What else? Okay. A corollary of this is the famous theorem, intermediate value theorem. Maybe I should write this as a theorem, and then I'll do okay. All right. So let f. So this is the intermediate value theorem. Value theorem. Okay. So let f be a continuous function. Where X is a connected space. If A is in f of x and B is in f of x, then okay, maybe I should write it. If let's say A is equal to f of x0 and B is equal to f of x1 for some x0 and x1 in x, then for any C in AB, there is some x in x with f of x equals c. So this means what? If a function defined, if it is continuous and defined on a connected space, real valued function, and if this function takes two values, a and b, then it takes all the intermediate values. Okay, if it takes a value a and another value b, then it takes all the intermediate values. Why is that? Well, because proof is very easy. Since f is continuous, and x is connected, its image f of x is a connected subset. Of connected subset of R, but we have just seen that connected subsets of R are just intervals. Hence, f of x is an interval. But interval means what? Whenever you have 2 points between them, then they contain all the interval. Uh, by assumption, AB, which is this interval f of x0, f of x1, lies inside I, right? This is an interval. This is the No, by assumption I have this. By assumption, uh, a, which is f of x0, is in I, and b, which is f of x1, is in I, but I is in interval. Since I is an interval, the whole interval AB must lie inside A. In particular, uh, C, which is an element of AB, is inside I, which is f of x. So there is some x in x with f of little x is equal to c, because c is inside f of x. Okay, so this is the general intermediate value theorem. If I have a connected metric space and a continuous function defined on X with values in the metric space R, then the image of F is an interval. Therefore, if it contains 2 points A and B, then it contains the whole interval AB. Okay. And this gives us as a corollary the intermediate value theorem in calculus. So if f, let's say, from R to R is a continuous function, and let's say f of x0 is equal to A and f of x1 is equal to B, uh, okay, let me say, and C is in AB, then there is some x in x0, x1 with f of x is equal to c, right? So I just, okay, x0 here, x1 here. Let's say this is A, this is B. Okay, this is a continuous function. What we are claiming is this: if I take any point here, C, then there is some x here, so that f of x is equal to c. Okay, this is the form we have seen in calculus course, right? This is the form of the intermediate value theorem we have seen in calculus course. All right. Okay, what else? Okay. Okay, so let E be a connected subset of a metric space. X if uh, F is a subset which lies between E and E closure, then F is also connected. Okay, so if you have a connected set, uh, its closure is also connected, and moreover, anything between that subset and its closure is also connected. Okay, and proof is the following. All right, suppose we have two open sets A and B of X with F lies inside A union B and this intersection is empty. Let's assume this. So I have two open sets whose union covers F, but intersections of these with F common intersection is empty. Okay. Now, since E is a subset of F and F is a subset of A union B, we have E intersection A intersection B is empty because E is connected. Okay. Right? Because if this is not empty, then it would mean that E has some points from wait a minute. Okay, we have E connected is a subset of this. Oh yeah, I have this. Uh, F is a subset of A union B. Sorry. Uh, oh, wait a minute. I assume what? E is connected, and we would like to show that F is connected. So I take open sets like this. E is a subset of this. Oh, okay. But this intersection is empty, and this intersection, uh, since we have this, E intersection A intersection B lies inside A intersection F intersection A intersection B, but this intersection is already empty, so that A intersection A intersection B is empty. Okay, yeah. Okay, since E is assumed to be connected by assumption, uh, E must lie uh, either must lie completely either in A or B, right? Because E is a connected set and E is contained in this union, and the intersection of E with these two open sets, the common intersection is empty. So there is only one step from E to be disconnected. What is that? E should have either no intersection with A or no intersection with B. This means that E must lie completely in A or completely in B. Without loss of generality, let's assume that without loss of generality, assume that A intersection E is empty, which means what? So B is a subset, no, E is a subset of B. In other words, E lies completely in B. Okay, I assume one of them. But then we have what? Okay, this means what? This means E is in particular x minus A, and A is closed. Therefore, x minus A is a uh, A is open. Therefore, x minus A is closed, where x minus A is a closed subset. So E is contained in this closed subset, but if a subset lies inside a closed set, then its closure lies in that closed set, because closure is the smallest closed set containing that subset. Hence, E closure is in x minus A. Okay? But then we must have what? Uh, so uh, E closure intersection A is empty. Therefore, hence F closure A is empty because F is in E closure, so that F lies completely inside B. But you see what we have obtained. We started with two open sets containing F. Their union is containing F, and the intersection, triple intersection, empty. And we have seen that F lies completely in one of them. It lies inside B, right? So whenever I have two open sets, AB as above, then F lies inside one of them. Okay? This implies that, hence, F must be closed. Must be connected. Okay, because whenever I have a separation, well, a candidate for a separation, F lies completely inside one of the open sets. Okay, and this finishes the proof. Okay, I think we may stop at this point. So next time I'll start with so-called connected subsets, connected components, sorry, and I'll talk about arcwise connected sets and so on. Okay, yeah. Okay, yeah. I have like 7 minutes, uh, or maybe let me start a little bit. Do you have any questions so far? I can answer your questions if you have any questions. Okay, so in the remaining 7 minutes, let me give you a definition. Let x, y be points in some metric space. If there is some continuous function uh, gamma ab x, so defined on some interval ab, with the following property, with gamma a is equal to x and gamma b is equal to y. Uh, we say that uh, x and y are connected by the path gamma. Okay, so we have this, right? AB, and I have a function, and this is gamma A, and let's say this is gamma B. Okay, so in this case, the points x and y are connected by the path gamma. If all the points of x are connected to each other by paths, then we say that x is path connected. All right, so if any 2 points of x are connected by a path, if I can find a path between any 2 given points, uh, then we say that x is path connected. Okay. So this is another definition, path connected. What is the relation to being connected? Here is the result proposition. Any path connected space X is connected. Okay, so let me prove this next time. So this proposition implies that being path connected is something stronger than connected. Okay, and later we will see some examples that there are connected spaces which are not path connected. So your space can be connected. It has one piece, okay, namely, but there might be some points on this space so that you may not find a path from one point to another, okay? Uh, this is like, you may have 2 points on a length and there might be no, for example, path from one point to another. So you have to go from one point to another by either a boat or plane because there are no paths, okay? But both points belongs to the same maybe length, okay? So it's something like that. All right, let me stop at this point. Next time I'll prove this proposition and continue.